Hello there, and welcome to the Sleep Science Calm Stories. I'm so glad you found your way here tonight. Maybe you're already lying comfortably somewhere, perhaps under a blanket, or maybe you're just beginning to settle down after a long day. Wherever you are, and whatever kind of night it happens to be where you are in the world, this is simply a quiet place to rest your attention for a while. Tonight, we're going to spend some time with a very unusual kind of star, not the kind of blazing, dramatic star you might imagine when you think about explosions or supernovae, but something much quieter, something smaller, something that, in many ways, represents the calm final chapter in the life of an ordinary star. These stars are called white dwarfs, and although the name might sound a little mysterious at first, the idea behind them is surprisingly gentle. They are not newborn stars beginning their journey. They are the quiet remains of stars that have already lived long and luminous lives. If you enjoy calm explorations of science and the universe like this, you're always welcome to subscribe to the channel. But for now, you can simply relax and listen. There's nothing you need to remember tonight, nothing you need to follow closely. If your attention drifts, that's completely fine. These ideas will still be here, moving slowly along. Whether you catch every detail or not, you can simply listen loosely. Across the night sky, the stars often appear steady and unchanging. From Earth, they look almost peaceful, small points of light that seem to sit quietly in the darkness, barely shifting from night to night, but deep inside each of those distant lights, something extraordinary is happening. Stars are not static objects. They are immense spheres of matter held together by gravity, with temperatures in their centers so high that atomic nuclei collide and merge together. This process is called nuclear fusion. In the heart of a typical star, hydrogen atoms combine to form helium. And when they do, a tiny amount of mass is converted into energy. That energy radiates outward through the star and eventually escapes into space as light and heat. The light that reaches your eyes from a star may have begun its journey thousands, sometimes millions of years ago, and all of that light began as nuclear reactions deep inside a stellar core. It may seem like the kind of thing we should already know, and yet it's still quietly astonishing. The stars that look so calm in the sky are, in reality, enormous furnaces of nuclear activity. And yet, despite all that energy, most stars spend the majority of their lives in a kind of delicate balance. Gravity pulls the star inward, constantly trying to compress it. Fusion pushes outward, producing energy that resists that collapse. For long periods of time, these two forces settle into a quiet equilibrium. The star neither expands dramatically nor collapses. It simply shines. Our own sun is in this stage right now. Astronomers sometimes call it the main sequence phase of stellar life. But you don't need to remember the term. What matters is the idea. A star can spend billions of years living in this balanced state. Billions. From a human perspective, that's almost impossible to imagine. Entire civilizations could rise and fall thousands of times over, while a star continues calmly burning hydrogen in its core. And during this immense stretch of time, the star appears almost unchanged. But slowly, very slowly, something begins to shift, because even stars do not have unlimited fuel. Deep inside the core, hydrogen atoms are gradually being fused into helium. The process is incredibly efficient, but it is not endless. Over millions and billions of years, the amount of hydrogen in the star's center begins to decline. At first, nothing noticeable happens. The star still shines. Gravity and fusion remain in balance, but eventually, the fuel in the core becomes too scarce to sustain the same reactions. And when that happens, the delicate balance inside the star begins to change. Fusion slows in the center. Gravity, which has always been pulling inward, begins to gain the advantage. The core of the star slowly contracts, and as it contracts, it heats up. This might sound strange at first, but compression tends to increase temperature. The same way a bicycle pump becomes warm when air is squeezed inside it, the shrinking core becomes hotter and denser. Meanwhile, the outer layers of the star respond in a completely different way. Instead of shrinking, they begin to expand. The star swells outward, becoming what astronomers call a red giant. From the outside, this transformation can be enormous. A star that once looked similar to our sun can expand hundreds of times its original size. If our sun ever reaches this stage, and astronomers believe it will, billions of years from now, its outer atmosphere may stretch far enough to engulf the inner planets of our solar system. Mercury would likely disappear first. Venus would follow, and Earth itself might eventually be caught inside the swollen outer layers of the aging sun. But even during this vast expansion, something else is happening quietly inside. At the very center of the star, the core continues to contract. Gravity presses inward. The material there becomes denser and denser, and slowly, the conditions begin to form something entirely new. The future white dwarf is beginning to take shape, not as a separate object yet, but as an increasingly compact core hidden deep inside the enormous red giant. If you imagine the star at this stage, it's a little like a glowing cloud surrounding a dense, shrinking heart. The outer layers are enormous and diffuse. The inner core is small and growing steadily heavier. Eventually, another quiet transition arrives. The outer layers of the star begin to drift away into space. This process can take thousands of years, sometimes longer. Gas slowly escapes the star's gravity, spreading outward into the surrounding darkness. When illuminated by the remaining heat of the central core, these clouds can glow in beautiful colors. Astronomers call these expanding shells planetary nebulae. The name is a little misleading. They have nothing to do with planets. Early astronomers simply noticed that some of these objects looked round and planet-like through early telescopes, and the name stayed. In reality, they are the fading outer atmosphere of a dying star. From far away, they can appear as glowing rings, delicate bubbles of gas slowly expanding through space. At their centers, something remarkable remains, because when the outer layers drift away, they leave behind the dense core of the original star, and that core is what becomes a white dwarf. A white dwarf is not a large star. In fact, one of the most surprising things about them is how small they are. Most white dwarfs are about the size of Earth. Just imagine that for a moment. A star that once stretched millions of kilometers across eventually collapses into an object roughly 12,000 kilometers in diameter, about the size of our planet. And yet, despite that small size, it still contains a large fraction of the original star's mass, often something close to the mass of our sun. It's easy to miss how strange that really is, because compressing that much matter into such a small volume produces one of the densest objects in the universe. Matter inside a white dwarf is packed together in ways that rarely occur anywhere else. If you could somehow collect a tiny spoonful of that material and bring it back to Earth, it would weigh many tons, far more than any ordinary metal or rock. This extraordinary density is the result of the immense gravitational collapse that created the white dwarf in the first place. When the star's outer layers drift away, gravity continues pulling inward on the remaining core. But something very interesting happens during that collapse. The star does not shrink forever. At a certain point, another form of pressure begins resisting gravity, and that strange balance is what allows the white dwarf to exist as a stable object. It's a quiet remnant of stellar life, no longer powered by fusion, no longer expanding or collapsing dramatically, just a dense, glowing ember of a once much larger star. And even now, as it slowly releases the heat it still holds from its earlier life, the white dwarf continues shining faintly in the darkness of space, not with the blazing intensity of a young star, but with a calm, steady glow, the kind of glow that can last for billions of years. And in the next part of our journey tonight, we'll look a little more closely at what makes these tiny stars so dense, and why gravity compresses them in such unusual ways. But for now, if you feel yourself becoming a little sleepier, you can simply let the details drift by. There's nothing you need to hold on to. The stars have been shining for billions of years, and they'll continue their quiet work whether we notice them or not. So you can simply rest here for a moment, listening to the slow story of how even the brightest stars eventually become small, patient embers in the vast dark of space. And there's something else quietly surprising about these small stellar remnants. For all their incredible density, white dwarfs are also remarkably small. When astronomers first realized this, it caused a great deal of confusion. The idea that a star could collapse into something the size of a planet seemed almost impossible at first. Stars are usually enormous. Our sun, for example, is about 1.4 million kilometers across. That's large enough to fit more than 1 million Earths inside its volume. So, the idea that a star could shrink to something only about 12,000 kilometers in diameter felt deeply counterintuitive. And yet, that is exactly what happens. A white dwarf is roughly the size of Earth. Imagine compressing almost the entire mass of the sun into a sphere no larger than our planet. That is essentially what gravity has done. From a distance, these objects still shine with a pale white glow, which is where the name white dwarf comes from. But their brightness does not come from ongoing fusion reactions. The nuclear fire that once powered the star is gone. Instead, the white dwarf shines simply because it is still hot. It is releasing the heat stored during the earlier stages of the star's life. In a way, it is like the ember left behind after a fire has burned down. The flames are gone, but the coal still glows softly. If you could somehow see a newly formed white dwarf up close, it would appear dazzlingly bright. Many young white dwarfs have surface temperatures tens of thousands of degrees hotter than the sun's surface, but because they are so small, They do not release nearly as much total energy. Their light is intense but compact, like a small but brilliant bead in the darkness. And inside that small sphere, matter is packed together in ways that feel almost unfamiliar. The density of a white dwarf is so extreme that ordinary comparisons begin to break down. On Earth, even the densest materials, like gold or lead, are still mostly empty space at the atomic level. Atoms are built around tiny nuclei surrounded by clouds of electrons, and most of the volume inside an atom is simply empty distance between those particles. But inside a white dwarf, gravity compresses matter until atoms are forced far closer together than they would normally be. The atomic nuclei remain intact, but the space around them becomes dramatically reduced. Instead of neat, widely separated atoms, the interior of the star becomes something closer to a tightly packed lattice of nuclei, surrounded by a sea of electrons. It's a little like taking the ordinary structure of matter and gently squeezing it until the empty spaces nearly disappear. And the result is extraordinary density. A teaspoon of white dwarf material could weigh several tons if brought to Earth. Some estimates suggest even more, but of course, no such sample will ever be carried back here. The gravitational forces holding the star together would make that impossible. And besides, the conditions inside a white dwarf only exist because of the immense gravity compressing everything inward. Remove that gravity, and the matter would immediately expand again. From inside the system, it's hard to see the whole shape of what's happening, but astronomers have learned to infer these properties through careful observations and theoretical physics. The mass of a white dwarf can often be measured by studying the motion of nearby stars or companion objects. Its radius can be estimated through its brightness and temperature, and when those measurements are combined, they reveal something remarkable. The star must be incredibly dense, so dense, in fact, that gravity at the surface becomes extremely strong. If you could somehow stand on the surface of a white dwarf, which would be impossible for many reasons, you would feel gravity tens of thousands of times stronger than the gravity on Earth. A human body would not be able to survive that force. Even a small object dropped onto the surface would accelerate downward with enormous speed. But this intense gravity is precisely what keeps the star compact. The entire structure of the white dwarf exists because gravity has compressed its matter to extraordinary levels. And yet, something equally remarkable is happening at the same time. Because gravity is not winning completely, the star is not collapsing indefinitely. At some point during the collapse of the original stellar core, another force begins pushing back. Not heat, not radiation, not fusion. Instead, the resistance comes from something much smaller, from the behavior of electrons themselves. Deep within the star, electrons are packed extremely close together, closer and closer as gravity squeezes the matter inward. But electrons obey one of the quiet but powerful rules of quantum physics. Two electrons cannot occupy exactly the same quantum state at the same time. This rule is known as the Pauli exclusion principle. And while that might sound like a subtle technical detail, its consequences are enormous. Because when electrons are forced closer and closer together, they begin resisting further compression, not through heat or motion, but through the simple fact that the available quantum states are already filled. This resistance creates a pressure. Astronomers call it electron degeneracy pressure, and that pressure becomes strong enough to support the entire star against gravity. It may seem strange that a rule governing tiny subatomic particles could hold up an entire star, but the universe often works this way. The smallest scales and the largest scales turn out to be deeply connected. In a white dwarf, trillions upon trillions of electrons collectively produce enough pressure to halt the collapse of a star that once burned for billions of years. And the result is a delicate balance. Gravity presses inward. Quantum physics pushes outward. Neither side wins completely. Instead, the star settles into a stable state, a compact sphere of dense matter, glowing faintly with leftover heat. From the outside, it may look like just another dim point of light in the sky, but inside, it represents one of the strangest forms of matter that nature allows. And there is something quietly beautiful about that balance. A star that once shone with nuclear fire now survives because of the quiet rules of quantum mechanics. If your attention drifts for a moment here, that's perfectly fine. You don't need to hold on to the physics too tightly. You can simply imagine the idea. A small star, about the size of Earth, resting in the darkness of space, gravity pressing inward, quantum rules pushing gently outward, and between those two forces, a steady calm, a star that no longer burns, yet continues shining softly for billions of years. And there is still more to discover about these quiet remnants, because the relationship between their mass and their size turns out to be stranger than almost anything we encounter in ordinary life. In most objects we know, adding more mass usually makes something larger. But in the next part of our journey, we'll see that white dwarfs behave very differently. In fact, when a white dwarf becomes heavier, it actually becomes smaller. And that strange relationship between mass and size is one of the most unusual features of white dwarfs. In everyday life, objects tend to become larger when more material is added to them. If you add more clay to a ball of clay, the ball grows bigger. If you pile more snow onto a snowball, the snowball expands. Mass and size usually grow together, but white dwarfs do not behave this way. In fact, the opposite happens. When a white dwarf gains more mass, it actually becomes smaller. This idea puzzled astronomers when it was first understood. At first glance, it sounds almost impossible. How could adding more matter cause something to shrink? But inside a white dwarf, the physics is very different from the physics of everyday objects. Remember that the star is already held up by electron degeneracy pressure, the quantum rule that prevents electrons from occupying identical states. When more mass is added to the star, gravity grows stronger. That stronger gravity squeezes the material inside the white dwarf more tightly. The electrons become even more crowded, and as they are pushed closer together, their resistance increases. But the way that resistance behaves causes the star to compress further rather than expand. So the heavier the white dwarf becomes, the more tightly gravity compresses it. The radius decreases, the density increases, and the star becomes even more compact. From inside the system, it's hard to imagine something behaving this way. But nature often surprises us when matter is pushed to extreme conditions. A white dwarf is already incredibly dense, but a heavier white dwarf becomes denser still. It is one of those quiet examples where the universe gently reminds us that our everyday intuition only works within a narrow range of conditions. Beyond that range, the rules begin to shift. Astronomers eventually realized that this strange relationship could not continue forever. There must be a limit, a point where even electron degeneracy pressure could no longer resist gravity, and that limit does exist. It was first calculated in the early 20th century by a young astrophysicist named Subramanian Chandrasekhar. He discovered that there is a maximum mass a white dwarf can have while remaining stable. If a white dwarf grows heavier than about 1.4 times the mass of our Sun, the pressure created by electrons can no longer support the star. Gravity would become too strong. The star would collapse further. This boundary is now known as the Chandrasekhar limit. It is one of the quiet landmarks in astrophysics, a number that tells us where one kind of star must end and another must begin. Fortunately, most white dwarfs never approach this limit. The majority of them form with masses comfortably below it. They remain stable for immense stretches of time, supported by the strange but reliable rules of quantum physics. And inside those stars, the matter itself carries a memory of the star's earlier life. Most white dwarfs are made primarily of carbon and oxygen. These elements were created during the earlier stages of the star's life, when nuclear fusion was still active deep inside its core. During those active years, hydrogen fused into helium. Later, helium fused into heavier elements like carbon and oxygen. When fusion eventually stopped, those heavier elements remained behind. The outer layers of the star drifted away into space, leaving the dense carbon-oxygen core behind. So a white dwarf is, in a sense, the compressed ashes of a once-burning star, a quiet sphere made of the products of nuclear reactions that took place billions of years earlier. Inside the white dwarf, those carbon and oxygen nuclei form a tightly packed structure surrounded by electrons. It is not quite a solid in the ordinary sense, not quite a liquid either. It is a state of matter shaped by gravity and quantum mechanics working together. And despite its incredible density, the star is still very hot. A newly formed white dwarf can have a surface temperature exceeding 100,000 degrees Celsius. That is far hotter than the surface of our Sun. But because the star is so small, it does not radiate as much total energy as a large star would. So its glow is intense but compact, like a tiny, brilliant bead of light in the vast darkness of space. Over time, that heat slowly escapes. The white dwarf radiates energy into the surrounding universe. And because there is no longer any fusion in the core to replenish that energy, the star gradually cools. This cooling process takes an incredibly long time, billions of years, perhaps even trillions. During this slow cooling, the white dwarf steadily becomes dimmer and dimmer. Its bright white color slowly shifts. At first, it may appear bluish white, blazing with leftover heat. Later, it becomes pale white. Eventually, it may glow faintly red, and as time continues to pass, the star grows dimmer still. Astronomers have discovered something very useful about this gradual cooling. White dwarfs cool in predictable ways. Their temperature drops along well-understood patterns, and because of this, scientists can use them as cosmic clocks. If astronomers observe a group of stars, perhaps in a star cluster, they can measure the temperatures of the white dwarfs within that group. Some will still be relatively warm. Others will have cooled for longer periods of time. By comparing these temperatures to models of stellar cooling, astronomers can estimate how long those stars have been fading, and from that information, they can estimate the age of the entire cluster. In other words, the quiet fading of white dwarfs becomes a way of measuring the passage of cosmic time. A group of dim stars slowly cooling together becomes a kind of astronomical calendar. It is a gentle example of how the universe records its own history. The fading glow of ancient stars quietly tells us how long they have been there, and even after billions of years, the cooling continues. The white dwarf slowly releases the heat stored during the long lifetime of its parent star. The brightness decreases, the temperature falls, the glow softens. It's easy to imagine this process like a glowing coal slowly losing its warmth during the night. At first, the coal shines brightly, then it dims. Eventually, only a faint red glow remains. White dwarfs follow a similar path, but on timescales far longer than any human experience. Billions of years pass while these tiny stars slowly fade. Yet their story does not end immediately with cooling, because deep inside some white dwarfs, something remarkable may eventually begin to happen. As they lose heat, the matter inside them may slowly begin to crystallize. Deep inside some white dwarfs, the slow loss of heat leads to an unexpected transformation. Over immense stretches of time, the matter inside these stars may begin to crystallize. At first, that idea sounds surprising. We usually associate crystals with minerals on Earth: quartz, salt, ice, or diamonds forming slowly under pressure. But inside a cooling white dwarf, something somewhat similar may happen on a much larger scale. To understand why, it helps to imagine what the interior of a white dwarf is like. Earlier, we talked about how the star's matter becomes extremely dense. The carbon and oxygen nuclei that make up most of the star are packed very closely together, surrounded by a sea of electrons. At very high temperatures, those nuclei still move with a certain amount of energy. They vibrate, shift, and slide slightly within the dense structure of the star. But as the white dwarf cools, that motion gradually slows. The thermal energy inside the star slowly decreases as heat radiates away into space. And when the temperature drops far enough, the nuclei can begin settling into more ordered arrangements. Instead of moving randomly, they lock into regular patterns. A lattice, a crystal structure. This transformation happens extremely slowly, spreading gradually through the interior of the star as it cools further. In a way, parts of the white dwarf begin to behave like an enormous solid crystal. Astronomers believe this process is most likely to occur in white dwarfs made mostly of carbon and oxygen, which, as we've seen, are the most common ingredients left behind after sun-like stars finish their lives. If crystallization begins, it probably starts deep in the center of the star, where gravity compresses matter the most. From there, the crystalline structure may slowly grow outward over millions or billions of years. It's easy to miss how extraordinary that is. A star, once a vast nuclear furnace, gradually transforming into something closer to a giant crystal sphere, quietly cooling in the darkness of space. And there is another subtle effect that comes with this transformation. When atoms arrange themselves into a crystal structure, they release a small amount of energy. It's not explosive or dramatic, but it does add a little extra heat back into the star. So, as crystallization spreads through the interior of the white dwarf, the process slightly slows the star's cooling. The fading glow lingers a little longer. It's almost like a final quiet echo of energy inside the star. Even though nuclear fusion ended long ago, The internal rearrangement of matter briefly adds a little warmth back into the system. Astronomers have found evidence that this process may really be happening. Careful observations of certain populations of white dwarfs show small patterns in their brightness and temperature that match the predictions of crystallization models. Some stars appear to pause slightly in their cooling, lingering at certain temperatures longer than expected. That behavior fits well with the idea that internal crystallization is releasing extra energy. In recent years, astronomers studying white dwarfs in nearby star clusters have gathered more data supporting this idea. By comparing the brightness of thousands of white dwarfs, they can see subtle groupings that appear to mark stages of this slow crystallization process. Of course, the details are still being studied. The interiors of white dwarfs are not something we can observe directly, but the patterns we see from afar seem to match the predictions of physics remarkably well. It's another quiet reminder that even distant stars can reveal the hidden behavior of matter under extreme conditions. And if you pause for a moment and imagine it, the picture is strangely beautiful. A tiny star, only the size of Earth, slowly cooling across billions of years, deep inside. Its atoms quietly arranging themselves into vast crystalline patterns. No explosions, no violent change, just the slow organization of matter under the gentle influence of gravity and time. Elsewhere in the universe, other white dwarfs live somewhat more complicated lives because many stars are not alone. A large fraction of stars exist in pairs, orbiting one another through space. These systems are known as binary stars. Sometimes both stars evolve separately and eventually become white dwarfs. But in other cases, one star may age faster than the other. When that happens, the first star may collapse into a white dwarf while its companion is still a normal star. And if the two stars orbit closely enough, something interesting can begin to occur. The gravity of the white dwarf can slowly pull material away from the surface of its companion star. Gas from the larger star begins drifting toward the white dwarf, not in a straight line, but in a slow spiral. Astronomers call this structure an accretion disk. The gas circles the white dwarf, gradually moving closer and closer as it loses energy. Eventually, some of that material settles onto the surface of the white dwarf itself. Over time, the layer of gas grows thicker. Most of this gas is hydrogen, the same element that originally powered the star during its earlier life. But now, instead of existing in the enormous furnace of a stellar core, the hydrogen is collecting in a thin layer on the surface of the white dwarf. And because the gravity there is so intense that hydrogen becomes compressed and heated, for a long time, nothing dramatic happens. The gas simply builds up slowly. But eventually, conditions reach a critical point. The temperature and pressure become high enough for nuclear fusion to ignite again. This time, however, the fusion occurs suddenly and explosively. The accumulated hydrogen ignites in a powerful flash. Astronomers call this event a nova. For a brief time, the white dwarf brightens dramatically, sometimes becoming thousands of times brighter than before. From Earth, a nova may appear as a star that suddenly grows brighter in the sky. But unlike a supernova, this event does not destroy the star. The explosion only blasts away the thin layer of hydrogen that had collected on the surface. Once that gas is expelled, the white dwarf remains behind, still intact, still dense, still stable. Over time, the process may begin again. Gas drifts from the companion star. It spirals toward the white dwarf. it settles onto the surface, and eventually, another nova may occur. Some binary systems have been observed producing repeated novae over long periods of time. It is a quiet cycle of gathering and release. Even here, the white dwarf itself remains mostly unchanged, a small, dense ember at the center of a complex gravitational dance. And if your thoughts are beginning to drift a little now, that's perfectly fine. You can simply imagine these small stars scattered throughout the galaxy, some cooling quietly on their own, others orbiting companions, occasionally flashing brighter for a short time, but almost all of them following the same slow path, cooling, fading, waiting patiently across billions of years. And as we continue, we'll look at how astronomers first discovered these unusual stars and how they eventually realized that tiny particles, obeying quiet quantum rules, could hold up an entire star against gravity. Elsewhere in the galaxy, many white dwarfs live their long lives quietly and alone, but our understanding of them did not appear all at once. When astronomers first encountered these strange stars, they were deeply puzzled because the earliest observations did not immediately make sense. One of the first clues appeared in a very familiar place in the night sky, near the bright star, Sirius, the most luminous star visible from Earth. Astronomers noticed something unusual in the 19th century. Sirius did not move through space quite the way they expected. Its motion seemed to wobble slightly, as if something unseen were tugging on it. This kind of motion often means that a second object is nearby, orbiting invisibly. Gravity from the unseen companion pulls gently on the visible star, causing the motion to shift. Eventually, astronomers were able to observe that hidden companion directly. The object was given the name Sirius B. At first, it did not seem very impressive. Compared to the dazzling brightness of Sirius A, this companion star looked small and faint. Through early telescopes, it appeared as a dim point of light beside a much brighter one. But when astronomers began studying it more carefully, something surprising emerged. The light coming from Sirius B suggested that it was extremely hot, hotter than many ordinary stars. Yet despite that heat, it was very faint. That combination was difficult to explain. Normally, a hot star should shine very brightly, but Sirius B did not. The only explanation that seemed to fit the observations was that the star must be incredibly small. If a star is hot but small, it can emit intense light from its surface while still producing only a modest total brightness. When astronomers began calculating the likely size of Sirius B, the result seemed almost unbelievable. The star appeared to be roughly the size of Earth, yet its mass was comparable to that of our Sun. This implied a density far greater than anything known at the time. At first glance, it sounded impossible. It may seem like the kind of thing we should already know today, but a century ago, this idea was deeply unsettling for astronomers. Nothing in classical physics seemed able to explain how a star could be compressed so tightly without collapsing further. For years, Sirius B remained something of a mystery. Eventually, new ideas from quantum physics began providing answers. In the early 20th century, scientists were beginning to understand that the behavior of particles inside atoms followed rules very different from the familiar laws of classical mechanics. One of those rules, the Pauli exclusion principle, would turn out to be essential. It states that two identical electrons cannot occupy exactly the same quantum state. In ordinary materials on Earth, this rule rarely becomes important on large scales. Atoms remain comfortably spaced apart, and electrons have plenty of available quantum states. But inside a white dwarf, gravity compresses matter so strongly that electrons are forced extremely close together. Eventually, they begin to run out of available quantum states. And when that happens, a pressure develops. A pressure that does not come from heat or motion, but from the quantum properties of the electrons themselves. This pressure resists further compression. It pushes outward against gravity, and when enough electrons are present, which is certainly the case in a star's dense core, that pressure can become extraordinarily powerful, powerful enough to support the entire weight of the star. It is a quiet but profound realization. The stability of white dwarfs depends on the rules of quantum mechanics. Tiny particles obeying microscopic laws collectively hold up objects as massive as stars. At first glance, it sounds impossible, and yet, the equations describing this behavior match observations remarkably well. The calculated sizes of white dwarfs align closely with what astronomers see. The predicted relationship between mass and radius matches the stars that have been measured, and the existence of the Chandrasekhar limit, the maximum mass for a stable white dwarf, also follows naturally from this theory. Over time, white dwarfs transformed from puzzling anomalies into well-understood examples of extreme physics. They became laboratories for studying matter under conditions impossible to reproduce on Earth. And even today, astronomers continue learning from them because these small stars are incredibly common. In fact, the Milky Way galaxy likely contains billions of white dwarfs. Most of them are faint and difficult to detect. They no longer shine with the brilliance of young stars. Instead, they glow softly as they release the heat left over from earlier stages of stellar life. Many drift quietly through space alone. Others orbit companion stars in gentle gravitational dances. A few sit close enough to Earth that we can observe them in detail. Sirius B remains one of the best-known examples. It orbits its bright companion every 50 years or so, tracing a slow path through space. Despite its small size, its gravity is strong enough to influence the motion of the larger star beside it, and that quiet, gravitational partnership was the first clue that revealed its existence. Elsewhere in the sky, many more white dwarfs remain hidden among the countless stars of the galaxy. Some are relatively young, still glowing brightly with leftover heat. Others are much older, their light fading slowly as they cool. If we could somehow watch the Milky Way across billions of years, we would see more and more stars completing their lives and becoming white dwarfs. It is the common fate of most stars. Even our own sun will follow this path someday. Several billion years from now, long after its red giant phase has passed and its outer layers have drifted into space, the remaining core of the sun will settle into a white dwarf. It will be small, dense, and still glowing faintly from the heat it once contained. The planets that remain in the solar system will orbit a dim white star rather than the bright sun we know today. From inside the system, it would feel like an entirely different era, but the star itself would remain stable for an immense length of time, cooling slowly, quietly, patiently, and that patience is one of the defining qualities of white dwarfs, because once they form, their evolution becomes incredibly slow. They do not burn new fuel. They do not expand or collapse dramatically. They simply release heat, year after year, million after million, billion after billion, until their glow gradually fades into the deep darkness of space. If you imagine the galaxy far in the future, it may contain vast numbers of these faint stellar embers, quiet points of fading light drifting through the spiral arms. And if your thoughts wander a little here, that's perfectly all right. You can simply picture those tiny stars scattered across the galaxy, small, dense, still glowing softly after billions of years. And as we continue our journey tonight, we'll explore what happens to these stars across the deepest stretches of cosmic time, when even their faint glow begins to fade toward darkness, and over truly immense stretches of time. The quiet cooling of white dwarfs continues. Unlike young stars, they have no internal engine creating new heat. There is no fresh hydrogen fusion in their cores, no new fuel being ignited. Instead, a white dwarf simply releases the heat it already contains. This process is very slow. The star radiates energy into space, and as it does, its temperature gradually falls. The glow softens. The brightness declines. The color slowly changes. A newly formed white dwarf may appear bright and white blue, radiating enormous heat left over from the final stages of its parent star's life. But over millions and billions of years, that intense glow begins to fade. The color shifts gently. White becomes pale yellow. Yellow drifts toward orange. Eventually, the star glows with a faint reddish light, like a coal losing its heat in the dark. And throughout this entire process, the star remains remarkably stable. There are no sudden structural changes, no dramatic collapse, just the quiet release of stored heat into the vast cold of space. Astronomers have spent decades studying this cooling process. By observing large groups of white dwarfs, scientists can compare stars that have been cooling for different lengths of time. Some are still relatively warm, others are much older and dimmer. When these observations are placed together, they reveal a pattern, a cooling curve that describes how white dwarfs fade over time. This curve allows astronomers to estimate how long a particular white dwarf has been cooling since it formed. And because white dwarfs form at predictable stages in the life cycles of stars, this cooling information can reveal something even more useful. It can help determine the ages of entire star populations. Imagine a cluster of stars that all formed around the same time, over billions of years. The more massive stars evolve first. They expand, shed their outer layers, and leave behind white dwarfs. Less massive stars remain on the main sequence for longer. So, within a cluster, astronomers can observe white dwarfs at different stages of cooling. The faintest and coolest white dwarfs in the cluster represent the oldest ones, the stars that became white dwarfs first. By measuring their temperature and brightness, astronomers can estimate how long they have been cooling, and that cooling time reveals the age of the cluster itself. In this way, white dwarfs become quiet cosmic clocks. Their fading light records the passage of time across billions of years. It is a gentle kind of timekeeping, not ticking seconds or minutes, but measuring ages of galaxies and star systems, and it works surprisingly well. Some of the oldest star clusters in the Milky Way have been dated in part by studying their white dwarf populations. The faintest remnants reveal how long those stars have been cooling. And that cooling tells a story stretching back nearly to the early days of our galaxy. From inside the system, it's hard to see the whole shape of that timescale. Human history spans only a few thousand years. Civilizations rise and fall across centuries, but white dwarfs cool across billions. Their fading glow becomes a record of deep cosmic time. And yet, even after billions of years, most white dwarfs are still far from completely cold. The universe itself simply hasn't existed long enough. Many of the white dwarfs we see today are still relatively warm compared to what they will eventually become. Astronomers believe that if we could fast forward the universe far enough into the future, these stars would continue cooling until they emitted almost no visible light at all. At that stage, they would become something called black dwarfs. A black dwarf would be the final cooled remnant of a white dwarf, a dense stellar core that has lost nearly all of its heat. But there is an interesting detail here. Black dwarfs do not exist yet. The universe is approximately 13.8 billion years old, but calculations suggest that it may take trillions of years for a white dwarf to cool completely into a black dwarf. That is hundreds of times longer than the entire current age of the universe. So even the oldest white dwarfs that exist today are still glowing faintly. They are still slowly releasing their heat, still drifting through space as quiet points of fading light. In a way, the universe is still in the early stages of this process. The long cooling of white dwarfs has only just begun. And if you imagine the far future of the cosmos, long after many of the bright stars have burned through their fuel, white dwarfs may become some of the most common visible objects in the sky. A galaxy filled with faint stellar embers, small remnants of stars that once burned brightly, each one cooling slowly, steadily, patiently, and even deeper within those stars. Subtle processes may continue unfolding. We spoke earlier about the possibility of crystallization inside white dwarfs. As the star cools, the dense carbon and oxygen nuclei inside may gradually arrange themselves into ordered structures. Over billions of years, more and more of the interior could transform into this crystalline state. Some astronomers have even suggested that very old white dwarfs could become almost entirely crystalline inside. It's a striking image. A star, once a glowing sphere of nuclear fire, gradually becoming something closer to an enormous cosmic crystal, silent, dense, and slowly cooling. If your attention drifts here, that's perfectly all right. You don't need to hold all of these ideas tightly. You can simply imagine a small star drifting quietly through space, still warm, still glowing faintly, releasing heat that began its journey billions of years ago. And even though the nuclear fire has long since gone out, the story of that star continues unfolding across immense stretches of time. Because in the universe, endings are rarely sudden. More often, they are slow transitions, long fading processes, quiet transformations that unfold patiently across the vast darkness of space. And there's another gentle way to think about these quiet, stellar remnants. A white dwarf is not really a new object in the universe. It is more like the memory of a star. Everything inside it was once part of a much larger, brighter system. The carbon and oxygen packed tightly in its interior were forged during earlier nuclear reactions while the star was still alive and burning. Those atoms were once part of an active stellar furnace. They moved in enormous convective flows deep inside the star. They were carried through layers of plasma, hotter than anything we can imagine on Earth. And now, after the star has shed its outer layers and the fusion reactions have ended, those same atoms remain behind, compressed, dense, quiet, in a white dwarf. The entire long history of a star has been folded inward into a compact remnant. It's easy to miss how strange that really is, because when we look at a faint star through a telescope, we see only a tiny point of light. It doesn't reveal the billions of years of change that created it. But inside that point of light lies the record of a stellar lifetime. Astronomers sometimes study white dwarfs precisely because of this. The composition of a white dwarf tells us something about the nuclear reactions that once happened in the star that produced it. Most white dwarfs, as we've mentioned, contain large amounts of carbon and oxygen. These elements are produced when helium nuclei fuse together during the later stages of stellar evolution. In stars somewhat larger than the Sun, additional reactions can occur, producing elements like neon and magnesium. When those stars eventually collapse into white dwarfs, those heavier elements remain inside the core. So, by studying the properties of white dwarfs across the galaxy, astronomers can learn about the earlier generations of stars that created them. In that sense, white dwarfs act as a kind of stellar archaeology. They preserve evidence of processes that took place long ago, processes that we cannot observe directly anymore. From inside the system, it might seem like the star has simply faded away. But in reality, the remnant still carries the chemical memory of everything that happened before. And sometimes, that memory becomes visible in surprising ways. In recent years, astronomers have discovered that some white dwarfs contain traces of elements that should not normally appear on their surfaces. Elements like calcium, iron, or silicon. These heavier elements are usually expected to sink quickly toward the star's interior because of the strong gravity. So, when astronomers detect them near the surface, it suggests that something unusual is happening. The most likely explanation is that small rocky bodies, asteroids, or fragments of planets are occasionally falling into the white dwarf. When those objects approach the star, the intense gravity can tear them apart. Their material spreads into a disk of debris orbiting the white dwarf. Over time, some of that debris spirals inward and settles onto the star's surface. The result is a thin layer of heavy elements that astronomers can detect with sensitive instruments. In other words, some white dwarfs appear to be slowly consuming the remnants of their former planetary systems. It's a quiet but remarkable discovery, because it suggests that planets can survive the dramatic red giant phase of their parent star, at least temporarily, long after the outer layers of the star have drifted away into space. Fragments of those ancient planetary systems may still orbit the white dwarf. Eventually, many of those fragments are pulled inward and destroyed. But while they exist, they leave chemical fingerprints in the light of the star. Those fingerprints allow astronomers to analyze the composition of distant rocky worlds. In a way, scientists can study the geology of alien planets that no longer exist, all from the faint light of a tiny white star. It's another example of how the quiet remnants of stars can still reveal surprising stories. Stories not just about stars themselves, but about the planetary systems that once surrounded them. If we imagine the far future of our own solar system, something similar might eventually happen. Billions of years from now, after the sun expands into a red giant and sheds its outer layers, the remaining core will settle into a white dwarf. The inner planets may not survive that transformation, but some outer objects, perhaps asteroids or icy bodies from the distant regions of the solar system, might continue orbiting the remnant sun. Over time, gravitational interactions could slowly send some of those bodies inward, and eventually, fragments of our solar system might fall into the cooling white dwarf that once was our sun. If distant astronomers were watching from another part of the galaxy, they might detect those same chemical fingerprints in the star's light, and from that faint signal, they might deduce that long ago, a planetary system once orbited there. It's a strangely comforting thought. Even after a star's bright life has ended, traces of its planets may still linger, quiet remnants of a much earlier era. And if your attention is drifting a little now, that's completely all right. You don't need to follow every step of the story. You can simply imagine these small stars scattered across the Milky Way, some cooling quietly on their own, some surrounded by thin disks of drifting debris, some occasionally pulling in fragments of ancient planetary systems, all of them small, dense, and slowly fading across immense stretches of time. And beyond our galaxy, the same process is unfolding again and again, because most stars in the universe will eventually follow this path. They will burn their hydrogen, expand into red giants, release their outer layers, and finally settle into quiet white dwarfs, small embers of stellar history, patient, stable, cooling slowly in the vast darkness of space. And as we continue drifting through this quiet story, we can begin to imagine something even larger, a future universe where these tiny remnants may become some of the most common surviving stars, a cosmos slowly filling with faint white points of cooling light. If we imagine the Milky Way far into the future, the sky itself would slowly begin to change. Today, when we look up at the night sky, most of the visible stars are still living in their long hydrogen-burning phase. They shine steadily, powered by nuclear fusion in their cores. But this stage of stellar life is not permanent. Every star is slowly using up its fuel. Some burn quickly and brightly, lasting only millions of years. Others burn much more gently and can continue shining for tens of billions of years. Stars like our sun fall somewhere in between. Eventually, over immense stretches of time, more and more stars complete their life cycles. They expand into red giants, they shed their outer layers, and they leave behind white dwarfs. If you could watch the galaxy across billions of years, the number of these small stellar remnants would slowly increase. More stars would finish their lives. More planetary nebulae would drift outward into space, and more white dwarfs would appear. Small, dense cores, quietly glowing in the dark. Astronomers believe that white dwarfs are already extremely common. The Milky Way may contain billions of them, but many are so faint that they are difficult to detect from Earth. Young white dwarfs are still relatively bright because they retain large amounts of heat. Older ones are much dimmer. They fade slowly as they continue cooling. Some are so faint that only the most sensitive telescopes can reveal them. It's possible that many of the faint points of light scattered across the galaxy are these quiet stellar remnants, stars that once shone much more brightly long ago. Even now, some of the closest stars to our sun are white dwarfs. One example is Sirius B, which we spoke about earlier. Another is a star known as Procyon b, the faint companion to the bright star Procyon. There are several others scattered within a few dozen light years of Earth. Each one is small, each one is dense, and each one is quietly releasing the heat left behind from an earlier era of stellar life. From inside the galaxy, it can be difficult to see how common they really are. But when astronomers build models of how stars evolve across billions of years, the pattern becomes clear. White dwarfs are the final destination for most stars in the universe. Any star with a mass up to about 8 times the mass of our Sun will eventually follow this path. That includes the vast majority of stars that exist. Only the most massive stars end their lives differently, collapsing into neutron stars or black holes after powerful supernova explosions. But those massive stars are relatively rare. Most stars live quieter lives, and they end those lives quietly as well. So in the long story of the universe, white dwarfs are not unusual. They are the most common stellar ending, a calm and stable state that can persist for extraordinary lengths of time. If you imagine the galaxy billions of years from now, the bright blue and white stars we see today will gradually disappear. Many of them will have already evolved into white dwarfs. The sky would slowly become filled with these faint stellar embers, tiny points of light, cooler than they once were, but still glowing softly. It's easy to overlook how patient this process is. A white dwarf may take billions of years to cool significantly, and even then, it continues glowing faintly. Long after its parent star has vanished from memory, the remnant core still lingers, quietly fading. Astronomers sometimes describe these stars as the long-lasting relics of stellar evolution. Relics is an interesting word. It suggests something ancient, something preserved from a much earlier time. And in many ways, that description fits. Each white dwarf represents a star that lived an entire life before becoming what we see now, a life that may have lasted billions of years. All of that history compressed into a sphere roughly the size of Earth. And when we observe these stars through telescopes, we are seeing the final stage of that long story, a quiet chapter rather than a dramatic ending. From inside the system, it's hard to feel the true scale of that timeline. But if you imagine the galaxy continuing to age, white dwarfs become more and more important. They accumulate. Generation after generation of stars eventually joins their ranks. And in the distant future, long after many bright stars have faded, these remnants may become some of the most common luminous objects remaining in the galaxy. Small, dense, still glowing faintly from the heat they carry. And if your thoughts drift a little here, that's completely fine. You can simply picture the Milky Way as a vast spiral filled with quiet points of light, some bright, some dim, and among them, countless tiny stars slowly cooling across billions of years, little embers scattered through the galaxy, each one marking the final stage of a star that once burned brightly in the distant past. And as the universe continues aging, these faint remnants will remain, cooling slowly, patiently, drifting through the quiet darkness of space. And there is something else quietly remarkable about white dwarfs. Even though they represent the final stage of most stars, they are not entirely cut off from the rest of the galaxy. In many cases, they continue to interact with their surroundings. Sometimes those interactions are subtle. A white dwarf might drift through thin clouds of interstellar gas, slowly moving along the orbit it inherited from the star that once existed there. Other times, the interaction is gravitational, because many stars form in pairs. A white dwarf may still have a companion star nearby. We spoke earlier about binary systems, where gas from one star flows toward the white dwarf. Those systems can produce novae, sudden flashes of brightness caused by hydrogen igniting on the surface of the dense remnant. But binary systems can also reveal something deeper about how white dwarfs behave. When two stars orbit each other, their gravitational pull affects their motion in ways that astronomers can measure very precisely. By carefully observing the way one star moves, scientists can estimate the mass of its companion. This is one of the key ways white dwarfs were studied in the early years after their discovery. When astronomers measured the mass of stars like Sirius B, they discovered something surprising. Despite its tiny size, the star still contained nearly as much mass as our Sun. That combination, solar mass packed into an Earth-sized sphere, confirmed just how dense white dwarfs truly are. And once those measurements became more accurate, the theoretical ideas about electron degeneracy pressure began matching observations more and more closely. It's one of those moments in science where theory and observation slowly come together. Astronomers measure the motion of stars. Physicists calculate how matter should behave under extreme pressure. And eventually, the two stories begin to line up. The numbers agree, the models make sense, and the strange idea of a tiny, incredibly dense star becomes something we understand much more clearly. Still, white dwarfs remain fascinating precisely because they sit at the edge of familiar physics. Inside them, gravity compresses matter far beyond the conditions we normally experience. Atoms are squeezed, electrons crowd together, quantum rules begin to dominate the structure of the star. It is one of the rare places where the physics of the very small and the physics of the very large meet directly. The behavior of subatomic particles shapes the structure of an entire star. And this connection leads to another interesting consequence. Because the internal pressure supporting the white dwarf does not come from heat, the star does not behave like a normal gas. Ordinary stars are made mostly of hot plasma. If their temperature changes, their structure adjusts. They can expand, contract, or respond dynamically to heating and cooling. But a white dwarf is different. Its stability does not depend strongly on temperature. The degeneracy pressure created by electrons remains, even if the star cools significantly. So, as the white dwarf slowly loses heat, its overall size barely changes. The star becomes cooler, dimmer, redder, but it remains almost exactly the same size. That is another one of those quiet oddities of these objects. A white dwarf can cool for billions of years without noticeably shrinking. It simply fades. It's easy to imagine this like a glowing coal that gradually loses its warmth but keeps its shape. Except in this case, the coal is a star, and the timescale is far longer than anything we experience in daily life. Billions of years pass while the white dwarf slowly releases the heat it once held. And during all of that time, the galaxy continues changing around it. New stars are born from clouds of gas. Old stars evolve and die. Spiral arms shift slowly as stars orbit the center of the Milky Way. But the white dwarf itself remains steady, quiet, patient. It simply continues its slow cooling. From inside the system, it's hard to see the whole shape of that timeline. Human history feels long when measured in centuries, but a white dwarf can remain visible for billions of years after its parent star has finished its life. The remnant star outlives the stage that created it, and that persistence is part of what makes white dwarfs so valuable to astronomers, because they remain stable for such long periods of time. They become reliable markers of the past. When astronomers study large populations of white dwarfs, they are essentially looking at the fossil record of stellar evolution. Each one represents a star that once lived, burned hydrogen, expanded into a red giant, and shed its outer layers. The white dwarf is what remains after all of that activity has finished. A quiet survivor of an earlier chapter in the galaxy's history. And if your thoughts begin to wander here, that's perfectly all right. You don't need to keep track of every detail. You can simply imagine the galaxy as a vast place filled with different kinds of stars, some newly born, some still shining in their long middle years, and many others, small, dense remnants, slowly cooling across billions of years, tiny points of light scattered through the spiral arms, little embers of ancient stars. And as we continue drifting through this quiet story, we can begin to imagine something even larger still, a time far in the future, when the bright stars we know today have mostly faded away, and the galaxy is filled primarily with these small, cooling remnants of stellar life. If we could move far enough forward in time, the night sky of the Milky Way would begin to look very different. Today, the galaxy contains a wide mixture of stars. There are brilliant blue stars burning quickly and brightly. There are yellow stars, like our sun, shining steadily in the long middle of their lives. And there are many smaller red stars that burn their fuel slowly, sometimes lasting longer than the current age of the universe. But as billions upon billions of years pass, this balance slowly shifts. The bright blue stars disappear first. They live fast lives and exhaust their fuel quickly, sometimes in only a few million years. They explode as supernovae, leaving behind neutron stars or black holes. The yellow stars follow later. Stars like our sun shine much longer, but even they cannot burn forever. Eventually, they expand into red giants and then shed their outer layers, leaving white dwarfs behind. The smaller red stars, the dim, long-lived ones, will continue shining for the longest time. Some of them may burn hydrogen for trillions of years, but even those stars will not last forever. And as the universe ages, more and more stars complete their lives and join the quiet population of stellar remnants. The Milky Way will slowly accumulate white dwarfs. At first, they will simply be part of the background of the galaxy, faint stars scattered among many brighter ones. But over time, their numbers will grow. Imagine the galaxy tens of billions of years in the future. Many of the bright stars we see today will already be gone. In their place will be a growing population of faint stellar embers, white dwarfs drifting through space, slowly cooling. The sky of that future galaxy might appear dimmer overall. Instead of brilliant young stars dominating the view, there would be countless small points of pale light, each one the remnant of a star that once burned brightly, each one cooling slowly across immense stretches of time. It's a quiet transformation. Nothing dramatic happens all at once. Stars simply finish their lives one by one, and each time they do, another white dwarf joins the galaxy. Astronomers sometimes describe this process as the gradual aging of the stellar population. A galaxy is not a fixed collection of stars. It is constantly changing. Stars are born from clouds of gas. They shine for long periods, and eventually they evolve into remnants over billions of years. The balance between young stars and old remnants shifts slowly. The Milky Way today is still relatively young compared to what it will become. Star formation is still happening in many of its spiral arms. Clouds of gas collapse and ignite new stars. Bright clusters appear, but in the far future, that process may slow down. Gas reserves will gradually be used up. New stars will become less common, and the galaxy may slowly fill with the quiet remnants of earlier generations. White dwarfs, neutron stars, black holes. Among those remnants, white dwarfs will likely be the most numerous, because most stars are small or moderate in size, and those stars all end the same way. They shrink into these dense stellar cores. Small stars, but incredibly long-lived. From inside the system, it might feel like the galaxy has become quieter. The bright blue stars that once lit up the spiral arms will be rare. Instead, the sky will contain a softer scattering of faint lights, white dwarfs glowing gently, still warm from their long histories, still releasing the heat they stored while they were active stars. And this slow cooling continues far beyond the timescales we normally imagine. Billions of years pass, then tens of billions, then hundreds of billions. Through all of this time, the white dwarfs gradually become cooler and dimmer. The bright white glow fades. The stars become faint red points. Eventually, they become so dim that they would be difficult to see even from nearby distances. But they still exist. Small spheres of dense matter, holding the mass of stars that once shone much more brightly. It may seem strange that the final stage of stellar evolution is so calm. When we think of stars, we often imagine explosive events, supernovae, gamma-ray bursts, violent collapses. But those dramatic endings belong mostly to the most massive stars. For the majority of stars in the universe, the ending is far quieter. They simply release their outer layers and leave behind a small, dense core, a white dwarf, no longer powered by fusion, no longer changing rapidly, just slowly cooling in the dark. And if you imagine drifting through the galaxy during that distant future, you might see many of these faint stars scattered through the spiral arms, some traveling alone, some still orbiting companion stars. Each one a quiet reminder of a star that once burned much more brightly. It's easy to miss how patient the universe is. Processes that seem enormous to us unfold slowly across unimaginable spans of time. Stars are born, they shine, they age, and eventually they settle into these small, quiet remnants, little points of light that can continue glowing long after their earlier brilliance has faded. If your thoughts wander here, that's completely all right. You can simply imagine the galaxy filled with these gentle embers, tiny stars, Earth-sized, dense beyond anything we experience on Earth, and still glowing softly across the vast darkness of space. And in the deepest future of the universe, even those faint lights may eventually fade further still. And as the universe continues aging, the slow fading of white dwarfs carries the story even further into the future. For billions of years, these stars simply cool. There are no sudden changes, no new bursts of energy from their cores. The nuclear reactions that once powered them are long gone. Only the stored heat of their earlier life remains. That heat escapes gradually into space. Each year, the star becomes a little cooler, Each century, it grows a little dimmer, and over millions and billions of years, the bright white glow that once gave these stars their name slowly softens. A newly formed white dwarf might shine with a sharp white-blue light, extremely hot and energetic. But as time passes, the color drifts gently. White becomes pale yellow, yellow becomes orange, and eventually, the star glows with a faint reddish hue. Astronomers sometimes describe this as the star moving down the white dwarf cooling track, a long path through temperature and brightness that stretches across cosmic time. But you don't need to picture charts or graphs to imagine it. It's easier to think of the star as a glowing ember. At first, the ember burns bright. Then slowly, gradually, its warmth fades. Except, in this case, the ember is the dense core of a star, and the fading takes billions of years. Even after enormous stretches of time have passed, the white dwarf still exists. It remains incredibly dense, still roughly the size of Earth, still containing the mass of a star, only its temperature has changed. The star has grown cooler and dimmer, yet even this cooling is not completely smooth. Inside the white dwarf, subtle processes continue unfolding. Earlier, we spoke about the possibility that parts of the star's interior may crystallize as it cools. Carbon and oxygen nuclei settle into orderly structures under immense pressure. That slow crystallization can spread through the star over immense spans of time. In a sense, the interior becomes more organized as the star ages. Matter that once moved in chaotic nuclear furnaces settles into quiet, crystalline arrangements. It is one of the calmest transformations in astrophysics, not an explosion, not a collapse, just the slow ordering of atoms inside an ancient star. And while this happens, the galaxy around the white dwarf continues changing. New stars may still be forming in distant clouds of gas. Other stars are reaching the ends of their lives and becoming white dwarfs themselves. The spiral arms of the Milky Way slowly rotate around the galactic center. Stars drift through the galaxy on vast orbits, lasting hundreds of millions of years. From inside the system, it might be hard to notice these slow changes, but over billions of years, the galaxy is never completely still. White dwarfs simply continue their quiet cooling while all of this unfolds. And because they last so long, they become some of the most enduring objects in the galaxy. A white dwarf may remain visible for far longer than the bright star that created it. The earlier phases of stellar life, hydrogen burning, red giant expansion, planetary nebula formation, all occur over relatively shorter periods. But the cooling of a white dwarf stretches across immense timescales. In that sense, the final stage of a star's life becomes its longest chapter. It's easy to overlook that. We tend to think of endings as brief, but in stellar evolution, the ending can last far longer than the active life that came before it. A white dwarf can glow softly for billions, even trillions of years, patient, stable, almost unchanged. From a certain perspective, these stars become the quiet background of the galaxy, a growing population of stellar remnants scattered throughout the spiral arms, some orbiting companions, others traveling alone through interstellar space, many too faint to notice unless we look carefully. And if we imagine the universe continuing far beyond the present day, white dwarfs may eventually dominate the stellar population. not because they are newly created, but because they last so long. Generation after generation of stars will end in the same way, each one leaving behind a small, dense core, each one adding another faint ember to the galaxy. Over immense stretches of time, the sky could slowly fill with these quiet remnants, a galaxy of cooling stars, dense spheres of carbon and oxygen slowly releasing their final warmth. And yet, even then, the process would not truly be finished, because the cooling continues, ever more slowly, ever more gently, until eventually, in the deepest future of the universe, white dwarfs may reach a final stage that has not yet occurred anywhere we can observe, a stage where the star becomes so cool that it no longer glows at all. Astronomers sometimes call these hypothetical objects black dwarfs, but for now, they remain only theoretical. The universe simply has not existed long enough for any white dwarf to cool that far. Even the oldest ones we know are still faintly warm, still glowing softly in the darkness, still releasing the heat stored from their ancient past. And that quiet persistence tells us something about the universe itself. The cosmos is not only a place of dramatic events, it is also a place of immense patience. Stars live, they burn, they fade, and their remnants drift through the galaxy for timescales far longer than human history. If your thoughts wander here, that's perfectly fine. You can simply imagine those small stars scattered across the Milky Way, tiny points of light, Earth-sized, incredibly dense, still glowing softly, long after the brilliant stars that created them have faded into memory. And as we continue drifting through this quiet story, we'll move even further into the distant future, where the faint glow of these ancient stellar embers begins to approach its final, almost unimaginable stage. And if we follow the story of white dwarfs even further forward in time, the universe begins to feel quieter still. The cooling continues, year after year, century after century, million after million. Nothing dramatic interrupts the process. The star simply radiates away the heat it once held inside its dense core, and as that heat slowly escapes, the white dwarf becomes cooler and dimmer. The bright white glow fades, the surface temperature drops, the color of the star continues shifting toward deeper reds. Eventually, after enormous stretches of time, the star becomes so faint that it would be difficult to see even from relatively nearby distances. Yet the star is still there, still dense, still about the size of Earth, still containing a mass comparable to that of the Sun. Only its temperature has changed. Only its brightness has softened. It is easy to imagine this stage like a coal at the very end of a fire. Earlier in the evening, the coal glowed brightly. Later, it dimmed to a softer red, and eventually, it became so faint that only the slightest warmth remained. Except in the case of white dwarfs, that fading process takes longer than entire eras of cosmic history. Astronomers estimate that it could take trillions of years for a white dwarf to cool completely. Trillions. That number is so large that it stretches far beyond the age of the universe today. Our universe is roughly 13.8 billion years old. But the full cooling of a white dwarf may take hundreds of times longer than that. So even the oldest white dwarfs we observe today are still relatively warm compared with what they will eventually become. Their cooling has only just begun. The universe itself is still too young for the final stage to exist. And that final stage has an interesting name, a black dwarf. A black dwarf would be the ultimate remnant of a star that once burned brightly, a white dwarf that has cooled so completely that it no longer emits visible light. No glow, no warmth detectable from afar, just a dense, cold sphere of matter drifting quietly through space. But for now, black dwarfs remain theoretical. No such objects exist yet. The universe simply hasn't had enough time. Every white dwarf that has ever formed is still somewhere along the long path of cooling, still releasing heat, still glowing faintly. And this idea leads to an interesting realization. If the universe continues aging far beyond its current lifetime, the sky itself will slowly change. The bright stars we know today will eventually disappear. Massive stars will explode and leave behind neutron stars or black holes. Sun-like stars will become white dwarfs, and those white dwarfs will continue cooling. Over immense spans of time, the number of glowing stars in the universe will gradually decline. The sky would grow darker, not suddenly, not dramatically, just slowly, steadily, as generation after generation of stars completes its life cycle. If someone could stand inside a galaxy trillions of years from now, the night sky might contain very few bright stars at all. Instead, it would be filled mostly with faint stellar remnants, white dwarfs cooling toward darkness, neutron stars slowly losing their heat, black holes drifting invisibly through space. From inside that distant future, the brilliant, star-filled sky we see today might feel like a memory of a much earlier cosmic era, a younger universe, one filled with bright stellar fire. But even then, white dwarfs would still remain, small, dense, quiet, still holding the mass of the stars that once created them. They would continue drifting through the galaxy on their long orbits around the galactic center. The spiral structure of the Milky Way might change over time. Stars slowly shift their positions as they orbit. Clusters dissolve. New gravitational patterns emerge. But the white dwarfs themselves would remain stable. They do not explode. They do not collapse. They simply exist, cooling slowly, patiently, releasing the last traces of warmth that began when the star was still alive. And if your thoughts wander here for a moment, that's completely all right. You can simply imagine those tiny stars scattered throughout the galaxy, Earth-sized spheres of dense matter, quiet embers of ancient suns, some of them glowing faintly red, some already dim enough that only the most sensitive instruments could detect them, and each one continuing the same long journey through time, cooling, fading, waiting, because in the universe, endings are rarely sudden. More often, they unfold as long, gentle transitions. A star burns for billions of years, then it becomes a white dwarf, and then, across trillions of years more, it slowly fades toward darkness. The story of a star does not end quickly. It simply becomes quieter and quieter until at last it becomes one more silent remnant drifting through the immense calm of the cosmos. And yet, even while white dwarfs quietly cool across immense stretches of time, the galaxy around them continues its slow, graceful motion. Stars do not remain fixed in place. Every star in the Milky Way is moving. Our sun, for example, orbits the center of the galaxy once every 250 million years or so. It follows a vast circular path through the spiral arms, carrying the entire solar system along with it. White dwarfs follow similar journeys. When a star becomes a white dwarf, it does not suddenly stop moving. The remnant simply continues along the orbit the star already had. So, a white dwarf may drift through the galaxy for billions of years, quietly circling the galactic center again and again. During that time, the galaxy itself slowly changes shape. Spiral arms shift and evolve. Star clusters form and gradually disperse. Giant clouds of gas collapse to form new stars in some regions, while in other regions, the gas grows thin and quiet. All the while, the white dwarfs continue their long cooling. It's easy to imagine them like tiny lanterns drifting through a vast city that is constantly rearranging itself. The lanterns grow dimmer with time, but they remain. From inside the system, it's difficult to see just how far these journeys carry them. A white dwarf that forms in one part of the galaxy may travel enormous distances across billions of years. It might cross spiral arms many times. It might pass near giant molecular clouds where new stars are forming. It might drift close to other stars, briefly influenced by their gravity, before continuing on its path. And occasionally, two white dwarfs may encounter one another in more complicated ways. In very rare systems, two white dwarfs can orbit each other as a pair. These systems are sometimes called double white dwarf binaries. Both stars are small, both are extremely dense, and both slowly orbit one another in quiet gravitational circles. Over long periods of time, something subtle happens in these systems. As the two stars orbit, they emit tiny ripples in space-time, known as gravitational waves. These waves carry energy away from the system. The loss of energy causes the stars to move gradually closer together. The change is incredibly slow. It may take millions or billions of years, but little by little, the orbit shrinks. The two stars spiral inward toward one another. Eventually, in some cases, they may merge. When that happens, the outcome depends on the total mass of the system. If the combined mass remains below the Chandrasekhar limit, the two stars may simply merge into a slightly larger white dwarf, a denser remnant, still supported by electron degeneracy pressure. But if the total mass exceeds that limit, the result can be far more dramatic. The merged star may become unstable, and under the right conditions, this instability can trigger a powerful explosion known as a Type 1a supernova. For a brief time, the star becomes extraordinarily bright, so bright that it can outshine entire galaxies. But these events are rare compared to the quiet lives of most white dwarfs. The vast majority simply continue cooling. They do not collide. They do not explode. They drift peacefully through the galaxy for billions of years. And in many ways, that quiet stability is what makes them so fascinating. White dwarfs sit at a calm intersection between gravity, quantum physics, and cosmic time. They are the natural outcome of stellar evolution for most stars. They show us how matter behaves when compressed to extraordinary densities, and they remain visible long after the bright stages of stellar life have passed. If you imagine the galaxy as a long story, white dwarfs are like the final pages of many chapters. The main events have already happened. The star has burned its fuel, expanded, shed its outer layers, but the remnant remains, a small, dense core holding the memory of that entire history. And even now, as it drifts quietly through space, it continues releasing the last of its stored warmth. If your attention wanders for a moment here, That's perfectly fine. You can simply picture the galaxy from far away, a vast spiral of stars slowly turning in the darkness. Among those stars are countless tiny white points of light, some bright, some faint, some already cooling toward deep red, each one the quiet ember of a once luminous star, each one following its long orbit through the galaxy, cooling, drifting, enduring, and as we move further into this quiet story, we'll begin to return to the larger perspective again, to the idea that white dwarfs are not just individual stars, but part of the long, patient rhythm of the universe itself. And when we step back and look at the universe as a whole, white dwarfs begin to feel less like unusual objects and more like part of a quiet cosmic rhythm. Stars are born, they shine for immense periods of time, and eventually, many of them settle into these small, dense remnants, again and again, across billions of years. The same story repeats. A cloud of gas collapses, a star ignites, light pours outward into space for ages. Then slowly, patiently, the star evolves. Its fuel runs low, its outer layers drift away, and what remains is a white dwarf, a compact ember of stellar history. It's easy to imagine this cycle unfolding quietly across the entire galaxy. In one region of space, new stars are forming from drifting clouds of hydrogen and dust. In another region, older stars are nearing the end of their lives, and scattered throughout the galaxy are countless white dwarfs, the long-lived survivors of earlier generations. From inside the system, it's difficult to see how steady this rhythm really is, but astronomers studying the Milky Way can trace it. They see young stars glowing blue and bright. They see middle-aged stars like our sun. They see aging red giants swelling outward, and they see white dwarfs quietly cooling. All of these stages are present at the same time, different chapters of stellar life unfolding across the galaxy. White dwarfs simply represent the final stable chapter for most of those stories. And because that final chapter lasts so long, the number of white dwarfs steadily grows as the galaxy ages. Each generation of stars leaves behind its remnants. Over time, those remnants accumulate, billions of them drifting through the spiral arms of the Milky Way, small spheres of carbon and oxygen, dense beyond anything we experience on Earth, still glowing faintly from the heat stored during their earlier lives. If we imagine traveling through the galaxy, we might pass near many of these quiet stars without even realizing it. Some are faint enough that they would appear only as dim points of light. Others may be hidden beside brighter companion stars. A few might be surrounded by thin disks of debris left behind by disrupted asteroids or ancient planetary systems. But almost all of them share the same basic nature. They are stable, they are dense, and they are slowly cooling. That quiet stability is one reason astronomers find them so valuable. Because white dwarfs change very slowly, they allow scientists to study processes that unfold across enormous timescales. Their cooling reveals the ages of star clusters. Their compositions reveal the nuclear reactions that once took place inside their parent stars. Their densities test our understanding of quantum physics and gravity. And sometimes, when they interact with nearby stars or drifting debris, they reveal surprising details about the remnants of planetary systems. So even though white dwarfs are the ending of stellar life, they continue to teach us a great deal about the universe. They are like small archives of cosmic history, each one preserving clues about the star that once existed before it. If your attention drifts a little here, That's perfectly fine. You don't need to keep track of every detail. You can simply imagine the galaxy filled with these tiny stars, Earth-sized remnants scattered through the spiral arms, some newly formed and still hot, others billions of years old and slowly fading, all of them part of the same long cosmic process, a universe where stars are constantly being born, living out their lives, and eventually becoming these quiet, stellar embers. And in that sense, white dwarfs are not really an ending at all. They are part of the long continuity of the cosmos, a reminder that the universe rarely stops or resets. Instead, it transforms. Energy becomes light. Light fades into warmth. Warmth slowly dissipates into the vast darkness of space. And through it all, the remnants of stars continue drifting through the galaxy, carrying with them the quiet memory of everything that came before. Small stars, dense and patient, still glowing softly across unimaginable spans of time. And as we move toward the final part of our quiet journey tonight, we can begin to return once more to the simplest image of all, a single white dwarf star, drifting slowly through the Milky Way, cooling gently in the deep silence of space. And when we return to that simple image, the story of white dwarfs becomes very quiet again. Just a small star, about the size of Earth, drifting through the galaxy. From far away, it would look like a tiny point of pale light, almost easy to miss among the countless stars scattered across the sky. And yet, inside that small point of light is the compressed history of a star that once burned brightly for billions of years. The white dwarf is the final stable form of that long journey, no longer expanding, no longer collapsing, just resting in a careful balance between gravity and the strange rules of quantum physics. Gravity presses inward. Electrons resist being pushed closer together, and between those two forces, the star remains stable. It is one of the quietest balances in the universe. If we could somehow travel close to one of these stars, we would see something both simple and extraordinary. The surface would shine with intense heat. Newly formed white dwarfs can be tens of thousands of degrees hot, but because the star is so small, it would not look like the enormous blazing sphere of a young star. Instead, it would appear as a brilliant, compact orb of light against the darkness of space. The gravity there would be immense, the density of the matter beneath the surface almost unimaginable, and yet the star itself would remain still. No roaring nuclear furnace, no violent storms, just a dense sphere slowly releasing the heat left over from its earlier life. And that release happens very slowly. A white dwarf cools across billions of years. Even after enormous stretches of time, it still glows faintly. Astronomers studying the galaxy have found many white dwarfs that are already billions of years old, and still they shine. Their light softer now, their temperature lower than when they first formed, but still carrying warmth from the distant past. It's easy to imagine the galaxy filled with these quiet remnants, some orbiting companion stars, some drifting alone through the spiral arms, each one the compact core of a star that once expanded, burned hydrogen, and shed its outer layers into space, and each one continuing its long cooling journey. From inside the system, it might be easy to overlook how patient this process is, but the universe moves at timescales far beyond human experience. Stars take billions of years to evolve. White dwarfs take billions more to fade. even the eventual black dwarfs, the cold final remnants, will not appear until the universe is vastly older than it is today. So the white dwarfs we see now are only partway through their story, still warm, still glowing, still drifting quietly through space, and in a way, they are reminders of something gentle about the universe. Not every cosmic process is violent. Not every ending is explosive. Most stars finish their lives quietly. They release their outer layers. They leave behind a small, dense core, and that core simply cools, year after year, million after million, billion after billion, a steady fading that unfolds across the vast calm of the cosmos. If your thoughts wander here, that's perfectly all right. You can simply picture that small star again, Earth-sized, dense beyond anything we know on Earth, floating silently through the galaxy, its light soft and steady, its heat slowly radiating away into space. And somewhere far in the future, trillions of years from now, that faint glow will finally disappear. The star will cool completely. Its light will fade into darkness, and it will become one more silent remnant drifting through the universe. But for now, the white dwarfs we see tonight are still glowing, still releasing the warmth they gathered during their long stellar lives. Small, patient embers scattered across the galaxy, quiet reminders that even the brightest stars eventually become gentle points of fading light. And if sleep is already beginning to arrive, you can simply let it come. There is nothing more you need to hold on to tonight. The stars will continue their slow stories whether we watch them or not. And you can simply rest here now and let the night carry you the rest of the way. Hello there, and welcome to the Sleep Science Calm Stories. I'm so glad you found your way here tonight. Maybe you're already resting somewhere comfortable, the room dim and quiet around you. Or maybe you're still settling in, letting the day slowly fade away. Wherever you are, this is simply a gentle place to rest your attention for a while. Tonight, we've been exploring one of the quietest endings a star can have. Not an explosion, not a collapse into something violent or dramatic, but a slow transition into something small, dense, and remarkably patient. A white dwarf. If you've been listening from the beginning, you may remember how these stars form. A normal star spends billions of years burning hydrogen in its core, shining steadily, while gravity and fusion balance each other. Eventually, the fuel begins to run low. The star expands into a red giant. Its outer layers drift away into space, and what remains behind is the compact core, the white dwarf, about the size of Earth, containing a large fraction of the mass of the original star. It's easy to miss how strange that really is. A star shrinking from millions of kilometers across, down to something no larger than a planet. And yet the mass remains. Gravity squeezes the matter inside until atoms are packed extraordinarily tightly. The star becomes incredibly dense, so dense that a teaspoon of its material would weigh many tons if it could somehow be brought to Earth. But the white dwarf does not collapse forever. Something pushes back against gravity, and that resistance comes from one of the quiet rules of quantum physics. Electrons cannot occupy the same quantum state, so when gravity compresses them closer and closer together, they begin to resist. This resistance is called electron degeneracy pressure, and it is strong enough to support the entire star. It may seem surprising that tiny particles, obeying microscopic rules, can hold up an object as massive as a star. But the universe often connects the smallest things with the largest in ways that feel almost poetic. Inside a white dwarf, the laws governing electrons determine the structure of an entire stellar remnant. The star settles into a stable balance, gravity pressing inward, quantum physics pushing outward, and between those forces, the star remains steady, no longer powered by nuclear reactions, no longer expanding or collapsing dramatically, just glowing softly with the heat left behind from its earlier life. If your attention drifts here, that's completely fine. You don't need to remember every detail. You can simply imagine that small star floating quietly in space, because after a white dwarf forms, its story becomes very slow. The star begins cooling. Heat escapes from its surface into the cold darkness of space. The temperature falls gradually. The color changes slowly from bright white to softer tones, pale yellow, then orange, then faint red. Over billions of years, the star becomes dimmer and dimmer. But even after enormous stretches of time, it still shines, still releasing the warmth stored from when the star was alive. Astronomers have learned a great deal by studying this slow cooling. Because white dwarfs fade in predictable ways, they can be used as cosmic clocks. The temperature of a white dwarf reveals how long it has been cooling. And by measuring many white dwarfs in a star cluster, scientists can estimate how old that cluster is. In this way, the fading glow of these stars quietly records the passage of cosmic time, and the story continues even deeper into the future. As the white dwarf cools further, the atoms inside may begin arranging themselves into crystalline structures. The interior slowly becomes more ordered, carbon and oxygen nuclei settling into a dense crystal lattice. It is a calm transformation, not explosive, not violent, just the slow organization of matter across billions of years. Some astronomers even describe these stars as becoming enormous cosmic crystals. And still, the cooling continues. Trillions of years may pass before a white dwarf finally loses almost all of its heat. At that point, it would become something called a black dwarf, a cold, dark stellar remnant that emits almost no light. But the universe today is not old enough for that stage to exist yet. Even the oldest white dwarfs we can observe are still glowing faintly, still releasing the warmth of their past. From a certain perspective, the universe is still early in the long story of these stars. White dwarfs are still partway through their slow fading. And if we step back and look at the galaxy as a whole, we can see how common they are becoming. Every star, like the sun, will eventually become one. Generation after generation of stars, finishing their lives and leaving behind these dense remnants, billions of them scattered throughout the Milky Way, some traveling alone, some orbiting companion stars, some quietly drifting through interstellar space, each one a small archive of stellar history, each one holding the mass of a star that once shone much more brightly. And if you imagine the galaxy far into the future, the sky might slowly grow dimmer as more stars become these quiet remnants. Fewer brilliant young stars, more faint embers, a galaxy of cooling white dwarfs drifting through the spiral arms. It's a peaceful image, not a universe ending suddenly, but one that changes slowly, gently, across unimaginable stretches of time. Stars live, they shine, they fade, and their remnants continue drifting through the vast calm of space. If your thoughts are becoming softer now, That's perfectly all right. You can simply picture one of those tiny stars again. A white dwarf, Earth-sized, incredibly dense, still glowing faintly after billions of years, floating silently through the galaxy, its warmth slowly radiating into the darkness. And if sleep is beginning to arrive, you can let it come. Gently. There's nothing more you need to follow now. The stars will continue their quiet journeys, whether we listen or not, and you can simply rest here and let the night carry you the rest of the way. Hello there, and welcome to the Sleep Science Calm Stories. I'm glad you're still here. Maybe you've been drifting in and out of the story tonight. Maybe some parts slipped by while you rested quietly. That's perfectly fine. These ideas don't need to be held tightly. You can simply let them pass through your thoughts, like distant stars moving slowly across the sky. We've been talking about white dwarfs, those small, dense remnants left behind after ordinary stars finish their long lives. And by now, you might be able to picture them. Not enormous blazing suns, not violent explosions, but something much quieter, a star about the size of Earth, dense beyond anything we experience in daily life, still glowing faintly from the heat gathered during billions of years of nuclear fusion. Even though the nuclear reactions have stopped, the story of the star continues. The white dwarf simply releases that stored heat slowly into space, and that slow release can last an incredibly long time. It may seem like the kind of process that should end quickly, but in the universe, time stretches differently than it does for us. A white dwarf can glow for billions of years after its parent star has already completed its life. Even after enormous stretches of time have passed, the star remains, cooling, fading, drifting through the galaxy on the same long orbit it followed before. Meanwhile, the galaxy itself continues changing around it. New stars form in giant clouds of gas. Older stars evolve and expand. Some explode as supernovae. Others shrink into white dwarfs just like this one. The Milky Way is constantly reshaping itself, but the white dwarf remains steady. It is one of the quiet survivors of stellar evolution, and if you imagine the galaxy from far away, you might see it filled with countless points of light, bright stars still burning, young stars just beginning their lives, and among them, many tiny white dwarfs cooling slowly in the darkness, each one holding the mass of a star that once burned brightly long ago, each one drifting patiently through the spiral arms. It's easy to overlook how gentle this ending really is. Most stars do not explode. Most stars simply finish their lives quietly. They shed their outer layers. They leave behind a compact core, and that core becomes a white dwarf, a dense sphere of carbon and oxygen, stable, patient, cooling slowly across billions of years. From inside the system, it might feel like the universe is full of dramatic events, and sometimes it is, but just as often, it is full of quiet processes unfolding slowly in the background. White dwarfs are one of those processes. They represent the calm after the fire, the long, steady, fading that follows the bright life of a star. And even though they are small, compared with the stars that created them, they remain for extraordinary lengths of time, long after the red giant phase has passed, long after the planetary nebula has drifted away. The white dwarf continues shining softly, a small ember in the dark. If you imagine the sky far into the future, billions or trillions of years from now, many of the bright stars we see today will have already finished their lives. The galaxy may contain fewer blazing suns. Instead, it may be filled with these faint stellar remnants. White dwarfs cooling slowly, neutron stars quietly spinning, black holes drifting invisibly through space. But among those remnants, white dwarfs will likely be the most common, because most stars in the universe end their lives this way. They do not vanish suddenly. They become these dense, quiet objects that linger across immense stretches of time. And if your attention drifts here, that's perfectly fine. You can simply picture one of those stars, small, dense, about the size of Earth, floating silently through the Milky Way, its light faint but steady, its heat slowly escaping into the cold darkness of space. Year after year, million after million, billion after billion, until one day, far in the distant future, even that faint glow will finally fade. But that moment is unimaginably far away. For now, the white dwarfs of the universe are still glowing softly, still carrying the warmth of stars that once shone brightly, and you can simply rest here with that quiet image. A tiny star drifting peacefully through the galaxy, cooling gently, patiently, just another small ember in the vast, calm night of the cosmos. And if you feel yourself getting sleepier now, you can let that feeling deepen. There is nothing else you need to do. The stars will continue their slow journeys, whether we follow them or not. And you can simply rest here now and let the night carry you the rest of the way. Hello there, and welcome to the Sleep Science Calm Stories. If you're still here with me tonight, perhaps listening softly as sleep slowly comes closer, we can spend a little more time with these quiet stars, white dwarfs, small remnants of once brilliant suns, drifting through the galaxy with extraordinary patience. By now, you may have an image of them in your mind, a star about the size of Earth, incredibly dense, still glowing faintly from the heat gathered during billions of years of nuclear fusion. But there is something else quietly remarkable about them. White dwarfs are not only the final stage of stellar life for most stars, they are also some of the most reliable objects astronomers can study. Because once a white dwarf forms, its structure becomes very stable. Its size barely changes. Its internal pressure remains supported by those same quantum rules we spoke about earlier, electrons refusing to occupy the same quantum state. And that stability means the star evolves in a very predictable way. It simply cools, slowly, steadily. The temperature drops over time. The brightness fades. The color gradually shifts toward deeper reds. But the star itself remains almost unchanged in size. In other words, a white dwarf is not constantly reshaping itself the way many living stars do. It is more like a steady beacon slowly dimming across cosmic time. And because this fading follows well-understood patterns, astronomers can use white dwarfs to measure the ages of stellar populations. Earlier, we mentioned how white dwarfs act as cosmic clocks. It's a lovely idea. Imagine a cluster of stars that all formed together long ago. Over time, the most massive stars evolve first and become white dwarfs. Those white dwarfs then begin cooling. Some have been cooling for a long time. Others formed more recently. When astronomers observe the cluster, they see a range of white dwarf temperatures and brightness levels. The faintest ones represent stars that have been cooling the longest. By studying this distribution, scientists can estimate the age of the cluster itself. It is a quiet method of timekeeping. No ticking, no moving hands like a clock, just the gradual fading of ancient stars. And from that fading light, astronomers can reconstruct billions of years of cosmic history. White dwarfs have helped scientists estimate the ages of some of the oldest star clusters in the Milky Way. Clusters that formed when our galaxy was still young. Clusters that have existed for nearly the entire lifetime of the universe. In this way, the fading glow of white dwarfs becomes a kind of astronomical archive, a record written not in words, but in temperature and light. If we imagine observing one of these clusters through a powerful telescope, we might see hundreds of faint white points scattered among brighter stars. Some of those points are newly formed white dwarfs, still very hot, still shining brightly. Others are much older, cooler, dimmer, each one marking a different moment in the long history of the cluster. And if your attention drifts a little here, that's perfectly fine. You don't need to follow every detail. You can simply imagine a quiet gathering of stars drifting together through the galaxy. Some young, some middle-aged, and some that have already completed their lives and become white dwarfs, tiny stellar embers glowing softly among the others. It's also interesting to remember that these remnants may outlast many of the stars around them. The earlier phases of stellar life, the bright, shining years, often last billions of years, but the white dwarf stage can last far longer. In some cases, trillions of years may pass before the star cools completely, so the final stage of a star's life may actually be its longest. That is one of the quiet ironies of stellar evolution. The brilliant phase we notice most easily is only part of the story. The long fading afterward continues far beyond it, and during all that time, the white dwarf remains a small, dense sphere of matter. Carbon and oxygen nuclei packed tightly together, electrons providing the pressure that holds the star up against gravity. The structure remains stable. The star simply releases its remaining heat little by little. From inside the galaxy, it's easy to miss how common these objects are becoming. But astronomers believe the Milky Way already contains billions of white dwarfs. Many are too faint to see with the naked eye. They hide among the countless stars scattered across the sky, quiet remnants of earlier generations. And in the long future of the galaxy, their numbers will continue growing. Every sun-like star that finishes its life will join them. Every moderate-sized star that sheds its outer layers will leave behind another white dwarf. Generation after generation, a growing population of dense stellar embers. If you imagine the Milky Way billions of years from now, the sky may be filled with these quiet points of fading light. Small, steady, patient, still drifting through the spiral arms of the galaxy, still cooling, still carrying the mass of stars that once shone brightly long ago. And if sleep is slowly arriving now, that's perfectly all right. You don't need to follow the rest of the story. You can simply hold on to the image of that tiny star again, Earth-sized, dense, floating quietly through the vast darkness of space, its glow faint but steady, its heat slowly radiating away into the universe. Just another quiet ember in the long, gentle story of the stars. Hello there, and welcome to the Sleep Science Calm Stories. If you're still listening, perhaps your thoughts are already drifting somewhere softer now. The room around you may feel quieter, the world outside a little further away. That's perfectly all right. We can simply spend a little more time with the calm image we've been carrying tonight. A white dwarf star, small, dense, patient, drifting quietly through the Milky Way. After the long, bright life of a star has ended, this is what remains. Not a dramatic explosion, not a sudden disappearance, but a slow and steady continuation. The outer layers of the star have already floated away into space long ago, forming beautiful clouds of gas that eventually disperse into the galaxy. What remains behind is the core, compressed, stable, still holding most of the mass of the original star. Inside that compact sphere, the atoms are packed together in extraordinary ways. Carbon and oxygen nuclei sit extremely close to one another, surrounded by a sea of electrons that help support the star against gravity. It's one of the rare places in the universe where the smallest rules of quantum mechanics hold up something as massive as a star. And yet the star itself appears calm. From far away, it simply looks like a faint point of light. No flaring surface. No giant storms like those seen on younger stars. Just a steady glow slowly fading across time. Even now, scattered across our galaxy, there are billions of these quiet remnants. Some formed recently, only a few million years ago. They are still extremely hot, shining with sharp white light. Others formed billions of years earlier. They have already cooled significantly, glowing with softer tones of orange or red. Still others are so faint that they are difficult to detect even with powerful telescopes. But they remain there, patiently cooling, following their long orbits around the center of the Milky Way, one quiet lap after another. It's easy to forget that our own sun will eventually follow the same path in about 5 billion years. Long after any human memory has faded, the sun will expand into a red giant. Its outer layers will drift away into space, and the remaining core will settle into the same stable state we've been talking about tonight. A white dwarf, small, dense, still glowing faintly as it slowly cools. By that time, the solar system will look very different, but the quiet remnant of the sun will continue drifting through the galaxy for billions of years more. That thought can feel strangely comforting. The universe changes constantly, but it does so with enormous patience. Nothing rushes. Nothing forces the ending. Stars simply move through their long life cycles, one stage, slowly giving way to the next. White dwarfs represent that final calm stage, not the fire of youth, not the dramatic swelling of old age, just a quiet ember remaining after everything else has settled. And if you imagine the galaxy far in the future, you might see countless tiny lights scattered across the darkness, white dwarfs cooling slowly, some still warm, some nearly dark, each one holding the mass of a star that once shone brightly billions of years earlier. A sky filled with ancient embers, small stars, quietly remembering the earlier brightness of the universe. If your attention drifts here, that's perfectly fine. You don't need to hold on to every detail. You can simply imagine that gentle image again. A tiny star, about the size of Earth, floating silently through the galaxy. Its glow faint but steady, its warmth slowly radiating away into the vast calm of space. Year after year, million after million, billion after billion, and all the while the galaxy slowly turns around its center, carrying those tiny stars along on their quiet journeys. If sleep is close now, you can simply let it arrive. There's nothing left you need to follow. The stars will continue their slow stories, whether we listen or not, and you can simply rest here now and let the night carry you the rest of the way. Hello there, and welcome to the Sleep Science Calm Stories. If you're still listening now, we've reached the very quiet edge of our journey tonight, and if you happen to drift off somewhere along the way, that's perfectly all right too. These stories about the universe are patient things. They don't mind if we listen loosely, or if parts of them slip gently past while we rest. Tonight we spent time with one of the calmest endings a star can have. The quiet life of a white dwarf, a small, dense remnant left behind after an ordinary star finishes its long, luminous journey. Earlier, we imagined how a star, like our sun, burns hydrogen for billions of years, shining steadily in the sky. Then, slowly, it expands into a red giant, releasing its outer layers into space. And when that long transformation is complete, the core remains, compressed, Earth-sized, holding the mass of a star. That compact core becomes the white dwarf, no longer powered by nuclear fusion, yet still warm from the immense energy of its past. A tiny star, continuing to glow as it gradually releases the heat it gathered during its life. We followed that quiet glow forward through time, billions of years of slow cooling, the bright white light softening into yellow, then orange, then faint red, eventually becoming so dim that only the most sensitive telescopes could notice it. And if the universe continues far enough into the future, trillions of years from now, even that faint glow may finally fade away, leaving behind something colder still, a black dwarf, a silent remnant drifting through space. But that moment is unimaginably far away. For now, the white dwarfs of our galaxy are still glowing softly, billions of them scattered throughout the Milky Way, some newly formed and still bright, others ancient and faint, all of them small stellar embers quietly drifting through the spiral arms. If we imagine stepping far outside the galaxy and looking back from a great distance, we might see the Milky Way turning slowly in the dark, a vast spiral of stars and gas and dust, bright young stars shining in some regions, clouds collapsing to form new ones in others, and among all of that movement, countless tiny white dwarfs glowing faintly as they cool, each one the quiet memory of a star that once burned much more brightly, each one continuing its long orbit around the center of the galaxy. It's easy to forget how patient the universe really is. The processes we've talked about tonight unfold across billions and trillions of years. Stars live, they age, they fade, and their remnants drift through space long after their earlier brilliance has passed. White dwarfs remind us that endings in the universe are rarely sudden. More often, they are gentle transitions. The fire slowly settles. The light softens. The star becomes a quiet ember in the dark. If your thoughts are very soft now, you don't need to hold on to any of these ideas. You can simply keep that last image with you. A small white dwarf star, about the size of Earth, dense and steady, floating silently through the Milky Way, its faint light slowly fading as the galaxy turns around it, and somewhere out there, countless others just like it. Tiny embers of ancient stars, glowing quietly across the vast calm of the cosmos. Thank you for spending this quiet time here with me tonight. If you enjoyed drifting through these gentle discoveries about white dwarf stars, you're always welcome to return again for more slow journeys through the universe and the natural world. But for now, there's nothing else you need to follow. The stars will continue their patient stories whether we listen or not. You can simply rest here now, and if sleep is already near, you can let it arrive gently. There is nothing more you need to do.